Hello, and welcome to this tutorial for BioXTAS RAW. In this tutorial, you'll learn how to create a configuration file for RAW. We cover the first step of that configuration file here, where we go over how to calibrate the beam center, X-ray wavelength, and sample to detector distance. Once you've done this and the next steps of the tutorial, you will be able to accurately reduce two-dimensional images to one-dimensional scattering profiles using RAW. So before we can start this, we need to set certain values in the raw options. So we're going to go to the options, advanced options. First, we're going to go to the image and header formats. You want to set the image format appropriately. For this beamline, the appropriate image format is Pilatus, which is the default, but you may have to change it for your beamline. Next, we're going to set the header format. This data was collected at the BioCat beamline at the advanced photon source. So I'm going to use that header format. If you're using a beamline, data from beamline that is not available in RAW, you'll have to write your own function to load it in and add it to the RAW code, or you can contact the RAW maintainers and we can help you with that. Next, we're going to go to the general settings. I'm going to turn off this flip detector image because I know that at this beamline I don't need either of these flip settings on in order to get the correct orientation of the image relative to what we'd expect it to be. I'm also going to turn on this hide controls just because it makes things a little more compact when you load in scattering profiles. We're going to go to the radial averaging next in the 2D reduction. What we're going to do here is we're going to set the detector to Pilatus 1M, which is the detector for this beamline. We could also change the other settings, but we're not going to. Now I'm going to click OK. That'll save the settings and close the window. The data we're going to use is in the calibration data folder of the RAW tutorial data available on the RAW website. So I'm going to show the silver behanate image just by clicking Show Image here. This is a calibration image. We use silver behanate as our calibrant to calibrate the sample to detector distance and the beam center on the image. Now, it turns out silver behanate has a wide dynamic range displayed on the image, so in order to see all of that at once, I'm going to go to the image display settings down here, change the image scaling to logarithmic, and click OK. And now we can see distinctly the whole image, and in particular we can see these rings. These rings happen at very well-defined locations based on the calibration standard that we're using. And so this allows us to accurately calibrate both the beam center and the sample to detector distance. Next, we need to open the centering and calibration window. I'm going to do that by clicking on the Tools menu and selecting Centering/Calibration. The first thing to check here is that the detector is set correctly. In this case it is, because we set the detector in the advanced options. You also want to check that you have the right standard set. For us, that's silver behanate or AGBH. Next, we're going to set the energy. At this beamline, we've measured it externally, and we know it's 12.0. Now we're ready to do the centering and calibration via the automatic centering and calibration method, which you see down here. So you can select which of the values above that you've already set you want to fix. In this case, we only want to keep the wavelength constant. We want to fit the sample to detector distance, the beam center positions, and the detector angles. I'm going to go ahead and click Start. So you see there's a control here for ring number. What this refers to is which ring in the profile you're going to find points for so that we can fit it. Rings are numbered sequentially out from the beam stop. It starts with 0, 1, 2, etc. Note that if your beam stop isn't actually on the image, you may have to figure out what the first ring you're seeing on the image is. It might not be the closest one to the beam stop. You could imagine if we'd only measured the left half of the detector, we'd have to start at ring 1. So, what we want to do is we want to find points in the ring, and we do this just by clicking near the center of the ring, and the program will automatically find points at the ring peak and add them to the plot here. Going to do the same thing for ring 2, or rather the second ring out, ring number 1. You'll notice that we have to click in each section of the detector. It doesn't propagate between the different detector panels. Finally, for the last ring, once we have all the points selected and we're happy with them, we can click Done. If we didn't like one of our selections, we can click Clear Last Selected Points and then re-click. If we don't like any of them at all, we can just click Cancel. Now I'm going to click Done. It's going to use those points in the ring to automatically calculate the beam center and the sample to detector distance, along with the detector rotation angles. You can see the values it comes up with up here. We have the X and the Y center, we have the sample to detector distance, we have the detector angles, and these have all been automatically calculated. On the plot, what we're seeing is this red dot is where it found the beam center to be, and the dashed red lines correspond to the silver behanate rings, and you can see they fall very cleanly on top of the measured calibration rings. So in this case, it looks like the automated centering and calibration did a good job. I do want to revisit some of the calibration values over here. This sample to detector distance, I always recommend measuring it by hand and verifying you get something close when you do the calibration. That just gives you a kind of extra assurance that nothing has gone seriously wrong. And then for these detector angles, 0.5 is a very small angle. And you can imagine that that's a reasonable tilt for the detector, just a little bit offset, misset. This detector tilt plane rotation looks enormous, 140, 141. It turns out that this isn't just a single angle. This is trying to represent multiple coordinates with a single angle. And so there are ranges over which it takes different meanings for the two different coordinate values. And so you shouldn't be shocked if you get a really large value for the angle here. It's probably fine. If you want to learn more about exactly what that is, this is using the Fit2D coordinate system for calibration, and you can look that up either in Fit2D or in the PyPhi manual, which is what we use for the calibration. Once we're happy with the fit, everything looks good, we just click OK, and that will save those coordinates in the raw options. At this point, we're done with the centering and calibration in raw, and we can move on to the next step of creating the configuration file. Normally we do this all at once, so I'm not going to save the configuration file now. You'll see how to do that in later steps of the tutorial for creating the configuration file. With that, that's the end of the tutorial. You should now know how to calibrate the beam center, sample to detector distance, and X-ray energy in RAW.